Thank you very much. Thank you for inviting me today to talk about something which is not about science, not about green functions. So just relax. The interesting part is over. And now we talk about computers, technology, and the HPC. The original title of this talk was Frontiers in High Performance Computing. I'm sorry, but I don't like frontiers, so I decided to change a little bit the title, and I tried to collect some ideas about what are the challenges in computing things, in particular with the focus on materials sciences. I work in Ciega, which is a place where there are a lot of computers. I think the most powerful in Italy and among the most powerful also in Europe. As I told you, now we talk about something which is completely different. So that will be less serious. I don't know if it will be interesting as much as the previous talks. I don't think so. But I will give you some information because this is something which is behind everything Yambo users are doing. I was fascinated that before, during the poll, one of the most interesting click topics was using Yambo on HPC computers. Okay, that will give you some ideas about how complicated it was and how complicated it will be to exploit the computers that are now in place. There are many challenges, and let's start with the most important. When we want to do some calculation, we want to use all these beautiful machines that we have, and we would like to use them in the most efficient way. The thing is, these machines are huge, so we wonder how much we can get from these machines. So when we want to use something, we typically, if we have a Ferrari, we would like to go very, very fast. Okay, so we have a Ferrari supercomputing machine, and we would like to get the best from it. But this is very difficult. It's very difficult for a lot of reasons. The problem is that the calculation that we translate from our papers into the application codes are not efficient as we would expect. In some cases, we would like the speed, but this is not the best that we can actually get from that computer. We could also make some theory, and when we talk about computers, theory takes the name of performance model, in the sense that, okay, let's suppose that we have an application, then we may wonder how the time is spent in the machine. Because if we have only the CPU, this is quite simple. Let's say it's simple. It's not. But it would be quite simple to model a CPU behavior because you put there your calculation, the CPU crunches the numbers, and that's it. When we have a supercomputer, we typically have a CPU. Now we have almost everywhere also an accelerator, so a GPU. We have several nodes. The nodes are interconnected by a network. So if we want to get all these elements together, we should say, okay, we have the machine in which we have some time that is spent on the CPU, some time is spent on the GPUs. And then we have the communication between the CPU and the GPUs that has some latency. Then we have the communication across the network that again has some latency. And then all these things should be put together. What is the result? The result is, okay, I have a huge problem. I want to use a huge system. So I would like to distribute my problem over the system. But the problem now becomes another one. The fact is that I have several things computed in several places, and all these pieces are interconnected. So I need from time to time to synchronize all together, and this operation is time consuming. This is in a nutshell the explanation why when I perform a calculation, and this is a Yambo calculation, I may see that, okay, I start with a number of nodes, it takes some time. I expect that when I increase the number of resources that I use to compute the same problem, the times decreases, which is true until a certain point. That is known as the saturation point. Why? Why? You see that the efficiency stop to decrease because all these parts that are the bad ones, the ones that limit my efficiency, start to dominate. The problem is that, yes, if everything was independent, if all the pieces were independent, okay, I could continue increasing my efficiency. But in the case that all the pieces should be somewhat connected, then the problem becomes critical. This, just to give you some reference names, this figure is known as the strong scaling. Strong scaling means I have a very big workload, and I start to distribute this workload across a number of nodes. And I see what is the scaling over time of this problem. There is another case in which, okay, I change my way to reason, and I say, okay, but let's suppose that when I increase the number of resources that I use to compute something, I also increase the size of my problem. This is the typical case, for example, of weather forecast. Okay, I have a machine with 1,000 nodes. I have a grid, which is a number of 1,000 points. If I have a larger machine, for example, 10,000 nodes, I can work with a finer grid. Okay? So I increase the size of my problem proportionally to the system size. Well, this is a very ideal case because it's a case in which, in principle, I could have some cases in which, okay, I have many cases, I increase the number of cases, communication is zero because each of these small problems are not independent, and then I will have a linear scalability. This is a very nice case because it will permit to not worry about the communication or synchronization problem. But this is also something that is not very wise because in this case, I would simply create a system in which all the pieces are not interconnected. And this is a case that, for example, works very well in cases where I don't have a high-speed network, but it's something like a grid-like computing. Okay, but the thing is now that the interesting cases for science are the ones in which I combine the necessity of scaling up a big problem and then to combine together a lot of these cases. So I have cases in which I have a strong scaling, so I should push the best efficiency from my resources, plus I have to combine several copies of my workloads in order to have replicas on which I can calculate, for example, statistics. One case that is very notable is something that happened during the last COVID pandemics, and there was the case for calculating, let's say, drugs for taking care of the COVID disease. And this was something that made the screening, which is something which is scalable because it's simply taking more copies of the science system of the number of 70 billions of ligands. Each ligand itself is a problem that should be solved with the most important efficiency. So this is something that we did using two systems. One was for EMI and the other from Cinega. That was a very nice challenge. Okay, so first challenge is to get the best performance from our code. The second challenge is to look at our systems and try to understand what is the evolution of the hardware, which is something which runs very fast. In this case, if no, you cannot remember, but in old times we had CPUs that were very simple. So one CPU was more or less monolithic object, Then we started to have more replicas, more modular replicas inside the same chip. And the first examples were the so-called dual cores. Now, if you look at your mobile phone, you have probably more than 32 cores inside the same chip. If you look at some systems that were used for HPC, you can reach like 64 or more cores inside the same chip. That means that even if you take a very, very small unit for calculation, this is itself very modular and very parallel. So we should find some way to parallelize our calculation even on a single chip. And this is done, for example, using something which is called the OpenMP approach, shared memory approaches. The other step was, okay, we want to push this concept of having more cores inside the same object, and that was done using the GPUs. GPUs were something that was added on top of the CPUs. The problem is, okay, you have the CPU. On the CPU, you have typically, let's say, not more than 32 cores. On GPUs, you can have more than hundreds of cores. Now, the problem was that you have parallelism at a very high level, but the other problem is that the CPUs and GPUs are physically separated. That induced the problem that since they had different memories, each time those were called to work together, they needed to exchange messages, and this is the latency problem that I mentioned before. Other problem, so far before the GPUs, we had typical programming languages such as Fortran, C, C++. When GPUs came up, we had the specific languages for each of these devices. Okay, so CUDA for NVIDIA GPUs, ROCm for AMD, and one API for Intel, plus some attempts to use multi-devices languages like Cocos, SQL, or OpenMP. So also programming now is challenging, okay? Even more challenging. Let me give you some good news. The good news is that apparently something is improving on this aspect. So the new GPUs have no more separation between themselves. So they share the same memory. So it seems that also moving some data from the CPU to GPUs will be more easy in the future. For example, the Grace Hopper systems by NVIDIA, the Instinct system by AMD. But okay, this is something which is happening now. We don't know if this is very effective, but this is an evolution of the hardware. Okay, the bad side of this is, okay, we wrote everything in our codes in order to work to move the data, and this is no more useful. Yes, that's it. You have to rewrite your application from time to time. I'm sorry, but this is the reality. In this respect, there is another challenge, which is related to the evolution of the hardware. Another bad news is the fact that the evolution of the hardware doesn't follow the necessities of scientists or HPC technologists. Okay, the evolution of the hardware follows the market. Since now the market is dictated by artificial intelligence, the hardware will be designed according to the artificial intelligence necessities. In this case, all the problems in artificial intelligence typically require arithmetic units with lower precision than what we were used to. We were using typically floating point 64 or 32. if you don't know what it refers to, this is the way in which a floating point number is represented inside the computer. So typically this is made by giving a bit for the sign, number of bits for the mantissa, and then number of bits for the exponent. This is the way in which a computer takes your numbers. You see that typically the double precision is something that gives a lot of bits for representing the mantissa. The trend now is to going to lower precision. That means a very low number of bits representing the mantissa and more bits for, and again, less bits again for the exponent, but this is extreme when you use, for example, floating point 8. Because all the typical cases from artificial intelligence does not require higher precisions. But we do. Okay, typically all our problems are problems that require a high level of precision. There is also another reason behind that, is the fact that these kind of representation are also energy expensive. Okay, so having more units at lower precision is more energy effective, and it permits to add a lot of these units. But as I said, what we need is a high precision. There are schemes that now permit to emulate floating point 64 or floating point 32 in lower precisions. This is a work made by Massimiliano Fadiga for Quantum Express. It takes inspiration for this work by Ozaki, called Ozaki schemes, that try to make a representation of a FP64 also using a lower precision unit. Hopefully this is going to make us survive with the new hardware, but this is again something that we need to do in order to adapt to the evolution of the hardware. As I said, another very important issue is the energy. Probably you have read this news about the fact that Microsoft plans to reopen a nuclear power plant in 3 Mile Island, which was also famous for a disaster. So you see that our memory is very limited in time. But okay, the point is that the energy is actually an issue. So when you want to build a data center, you should have some very strong energy constraints. This is, of course, reflected on a responsibility when we use the resources. So every time you submit a calculation, keep in mind that you are wasting energy. The same when you do something on ChatGPT, well, it's not for free, okay? So, and the issue about having something which is cost effective from the energy point of view is reflected to the fact that we should also think about not only power, not only time to solution, that is the most evident thing that we see, but also with the fact that how much power are we using. So something that some people are doing is try to make some plots taking care not only about the time to solution, but also to the energy to solution. If you put them together, you have the energy to solution. And this is something that is nice because it was done on a very different set of application, ranging from GROMACS for molecular dynamics to Quantum Espresso for ab initio calculation. And this is, for example, an analysis that say, okay, but we can save some energy if we sacrifice some time to solution. For example, decreasing the clock frequency of the processor. Okay, this is a very important aspect that we should also think about. Another point is the integration of the workflows. Okay, you are Yambo users. You know that when you start a Yambo calculation, typically you need to start from CONSHAM states. These CONSHAM states are calculated or with Abilit or Quantum Espresso. So, in a very nutshell, you're creating a workflow in which you calculate the CONSHAM states, and then upon them you can calculate your Yambo properties. Well, the point is that since now all the supercomputing systems are very large, it's even more easy to accommodate calculations that are not made by a single application, but are made by a lot of pieces that are between them interdependent. This is something that it's useful not only, for example, to combine replicas of the same simulation. For example, if you want to make screening of properties, but also if you have, for example, multi-scale problems, or if you want to create a chain of simulation that are interdependent with some relation between them. Well, in order to take all these kind of cases, now there are a lot of different solutions. Probably you already know what is AIDA, which takes the problem of creating a graph of dependencies. There are cases, okay, there are the counterpart of AIDA that is, for example, Fireworks in the materials project in the US. There are cases in which I may combine, for example, multi-scale simulation, for example, molecular mechanics with the quantum mechanics using something that is called MIMIC. There are cases in which I want to manage high throughput screening, for example, this is a case for rubrication analysis. So there are a lot of these kind of opportunities, but those are not very easy to realize because the thing is that behind all these machineries, you should have the same length, let's say, the same format in order to make the codes to talk to each other. And this is something which is not trivial in some cases. Okay. The data challenge. You know that now the big data problem is something which is quite something which is very popular among the talks. That's because on one side we are, when we perform some simulations, okay, we are creating data. Typically, we don't think much about that, but what we are doing is to create data. This data could be reused, okay, reanalyzed, and this is what fuels the artificial intelligence hype, okay? But in order to make the data be important, we should make them reusable. We should make them easy to be accessed. And this is, for example, something which is, I already talked about the interoperability. And this is what they call the FAIR principles. Now there are a lot of projects and a lot of money spent on these ideas of collecting and reuse data. For example, there is Optimade, there is the Materials Cloud, there is the A-Flow in the United States, there is Nomad. But this is something which is something that need a lot of attention because it's not trivial that if I have data, this is something that could be used without thinking about the content of the data, okay? It's not even easy to understand what is a given data. Okay, you know that there is the problem of metadata. Metadata are data describing data. Okay, and this is quite important because if you take something without knowing what is the pseudo that you use to generate it, how was structured the workflow for generating this data, what was the computer on which you generated this data, all this is meaningless. Of course, this requires some kind of infrastructure behind in order to collect and to structure all these things. But this is something which is growing in importance because, okay, you know that now AI is the dominant hype, at least in Europe. So the Commission the European Commission put a lot of money on it. If you look at the European system of, for funding EuroHPC, we have a so-called 7 pillars system, and you may see that applications are one of these pillars. So this is a kind of, let's say, interesting to see that applications and, for example, artificial intelligence are considered pillars of the same building. And it's also interesting to see that a recent code founded a lot of so-called AI factories. Well, the AI factories are supposed to be places in which data are used to produce support to industries, researchers. But the very question is how can we do something in this framework? Because I took a lot of time to really understand what is an AI factory, what is the purpose of a factory, and that was my face, I think, when I realized that this was the things coming out. But yeah, the thing is that the challenge is to survive artificial intelligence by integrating artificial intelligence in what we already do. There was this paper some time ago that, okay, started from the very beginning with empirical science, saying that, okay, that was the first paradigm, and then it came the theoretical science. Then in the 50s, we had the advent of computational science, and now we have at the time it was called the big data, now we would say artificial intelligence science, that is considered now the fourth paradigm. The point is that I don't see it as in this picture as a pillar on the same place of the application. What I see is the artificial intelligence as a tool that we may use to rely upon when we want to accelerate some kind of discovery. So I don't think that computational science replaced in the history theory or experiments. I think that computational science supported the theory and the experiments. At the same time, I see that maybe in some cases, artificial intelligence can be a support to accelerate the discovery together with the computational sciences and theory. So I don't see AI replacing the theory, also because AI requires the theory, requires the experiments, and requires the simulation data. But AI can help to accelerate discovery. Typical cases are, okay, if I perform some screening, what I can do is to have some artificial intelligence methods in order to accelerate the choice of what are the candidates for my search. Okay, so if I may take a picture, I asked the ChatGPT to generate a picture of what was my idea. Is that okay? We have the applications, the AI is standing on the shoulders of the applications, but I still see the applications as the giants in the science, and AI something that would help us if we may master these methods. I'm going to finish. In any case, don't worry, because Cinega, as this is my team, we are going to understand all these things in order to support the scientists, in order to try to see what we can do to make your life easier, despite what you may think, but we are trying to make things easier for you. So we are doing that thanks to the fact that these supercomputer centers exist, like Cinega, thanks to the fact that there are projects like MAX that are also funding applications like Yambo, and that are also projects that support the applications and the European framework. So thank you very much for your time. Thank you.
There was a big discussion after you started in the UK. So we have AI factory, and then just put the geographically the part which was suffering a lot of drop in the last heat wave. So I think there is a lot of challenge there, but. And the other thing that I heard is about a movement of research, let's say, we are obsessed about this going accurate, but actually, so we say, okay, we need larger machine, more efficient to go, more accuracy, and so, but to say, well, maybe at some point we have to stop the battery and say, that's the resource that we have. That's the accuracy we can get. It was also some efforts on actually just on the paper and say, oh, but this just show this with some more accuracy. So you said that, yeah. So I think this is some matter of discussion about considering, yeah.
Yeah, the point of the accuracy is very nice, because when something is for free, you take it without caring too much. Okay, so if you have a 14.64, you use that. But when it's maybe also faster, in addition to be more energetical, convenient, then you may try to say, okay, but this is not necessary to be at such high precision. I can do something which is less, without having results that are different. So yeah, that requires some kind of, let's say, awareness. And that is also something of which computer scientists have a role to pushing forward this kind of matters. Because of course, if I was keen to work on a paper, maybe I don't care about it. Yeah, but this is a point, sure.
Yeah. This is a real problem. Sometimes the maintenance downtime is too high.
Sorry, so that again?
The maintenance downtime is too high.
Yeah, I know. But yeah, you're
yeah. So if the software running behind the scene or men are less.
The point of the mentoring, this is true, but it's related to a couple of factors. Let's say one that is more easy to understand, and the other which is maybe better to hide. But the easy thing is that the more complex is the system, the more it's susceptible to have faults. Okay, so that means that it requires a lot of maintenance. The other is that, of course, in order to buy bigger machines, we would like to spend less. And that means that in some cases, the providers are not giving you the best quality of hardware. Also because you should understand that if I'm a provider of hardware, and on one side I have Amazon, and on the other one I have a Cinega or whoever, I would like to serve before Amazon, because Amazon is paying a lot of more money than what is Cinega doing. So this is the problem with the fact that, of course, the market is so wide, and we have a very, very small weight on this market. But we are doing our best to reduce the time for maintenance.
Just a small one. So, sorry. Yeah.
Sure. And another problem you
Yeah? Yeah, sure. No, I decided the problem, but that was my idea of what is. But no, I didn't let the possibility to charge GPT to the side. As long as I can.
So just a technical point. So you mentioned that in the most recent configuration, like the software, there is a kind of memory shared between the CPU and the GPU. And then that maybe in the future it will not be needed anymore to move the data between the. But is it true? Because in the end,
Yeah, so for example, using NVIDIA, you could also ignore the fact that the memories are physically different, because they have a logical address space which is the same.
but I mean, when I code with CUDA or whatever, I still have to
You can rely on the managed memory, which is something that doesn't take into account the fact that those are separated memories, but it is like a single space.
become more and more reliable.
Yes.
Okay.
The point is how much you are confident that that will work.